Good morning, good afternoon, or good evening, wherever you are. Thanks for coming to my SDC talk. Let's get started.
So let me start with a quick introduction. My name is Albert Chen, and I'm CEO of Callista.io. Prior to studying Callista, I worked at Western Digital, Microsoft, and various startups. Back in 2012, while working at Western Digital, I built the industry's first host managed SMR storage system. It ran on Linux kernel 2.6, and the drive had only a single SMR zone. Things had really changed since then. My contact information is listed here. Please give me a shout if you'd like to chat more about anything we cover here today, or if you're just bored from quarantining at home. Here's a quick preview of what we will cover here today. We will see how to enable host managed SMR everywhere, in distributed systems, databases, object stores, and a whole lot more. All without application changes or worrying about kernel version and dependencies. And we will see how by making a fundamental design decision to be device-friendly, we can enable consistent and predictable performance at scale. But first, let's go over the agenda. We will start with how current trends in storage have created some very interesting opportunities for host managed SMR and storage system software. Then we will discuss currently available options for enabling host managed SMR. What are the dependencies, limitations, and how we can improve on them. Finally, we will cover how we implemented these improvements in Callista Phalanx, which results in a user and device-friendly system with remarkable performance. So let's start with trends. The first and most obvious trend is that there is an explosive growth of digital data. This means we need cost-effective storage. Dollar per gigabyte must go down so we can store all the cat videos and memes that we create. However, this puts pressure on device makers to continuously coming up with larger, faster, and cheaper devices, which leads to increasingly complex architectures and usage models for new devices. For example, sequential write-only disks that trades off random write capability for higher capacity. However, the amount of I/Os hard drives can process per second have remained relatively constant as device sizes have increased. This results in a steady decrease in the amount of performance we can expect for a given amount of capacity, which leads to a problem of stranded capacity, as latency-sensitive workloads cannot fully utilize available capacity. If you are interested to learn more about this, I recommend Tim Walker's talk on multi-actuator drives in the storage architecture track. Taking a look at a more economic side of things, the average price for hard drives have remained relatively constant, despite the steady increase in unit capacity, which is actually good for storage consumers, but leaves limited margin for vendor innovation. However, all that being said, hard drives are still the best bang for the buck storage all around. Meanwhile, on the system side, the pursuit for cost efficiency and agility is pushing our IT infrastructures to be more dynamic and to operate with higher and higher tendency and commoditization. This leads to architectures and usage models that are unfriendly to storage devices, which causes performance and scalability issues. One example is the I/O blender effect, where virtualization transforms device-friendly large sequential read and writes into small, randomized, conflicting I/Os. And the fallout from this device and friendly behaviors can be noticeable on a single system, but extremely impactful at scale. For example, small random I/Os caused by the blender effect can dramatically increase the tail latency on the affected drives, which means we will experience an increase in variance on the amount of time it takes for a command to complete. While this behavior may be tolerable when our system is small and simple, component-level variabilities are amplified as our system increases in size and complexity. This is an issue that particularly affects interactive or latency-sensitive applications at scale. Consider a system where each server has a 99th percentile latency of 1 second. This means we can expect one request out of 100 handled by the server to be slow, 1 second or more. This doesn't sound too bad, does it? However, things escalate quickly if the system increases in complexity and size. If each user request is dispatched to 100 such servers in parallel, then approximately 63% of requests will take more than 1 second. For the mathematical curious, the 63% comes from 1 minus 0.99 to 100th power. And for some real-life impact, there are often repeated numbers that for every 100 milliseconds of latency, it costs Amazon approximately 1% in sales. And an extra half second of response time costs Google 20% in traffic. Finally, let's take a look at economics again. Most system bottlenecks can be alleviated by throwing more money at it. Add more hardware. In fact, sometimes it may be the more preferable solution. However, eventually, we will hit a point of diminishing and even negative returns. At that point, we will require a more fundamental change in investment to scale. Of course, we should always consider the cost to deploy new technologies. The benefit must outweigh the cost of adoption. In other words, the storage solutions that we implement should minimize any disruption and friction to the user. Okay, so all these brings us to this point. Storage systems and devices are becoming increasingly incompatible with each other. And this is causing performance and scalability issues. In this talk, we will introduce Callista Phalanx, a device-friendly storage system designed and optimized for software-defined environments and next-generation storage devices. We will see how it can help address this growing divide between devices and systems. But first, let's go over the current available solutions. SMR is a magnetic recording technology for increasing storage capacity. Host-managed SMR drives write data sequentially to the platter and overlaps new tracks on parts of previously written tracks. This results in higher track density to enable higher capacity points. Latency is also reduced when the host takes control of device state and data placement, enabling it to reduce tail latency, increase throughput, and manage performance at scale. However, host-managed SMR drives have a more restrictive usage model compared to conventional disks. They require hosts to write sequentially, align IOs to device zone boundaries, and actively manage zone states. In addition, host system software and hardware must be able to recognize and support the newly defined host-managed SMR device type and zone management commands. Consequently, users must make additional investment in their storage stack. Depending on configuration, users may need to update host bus adapter firmware, upgrade kernel version, modify existing applications, and/or install additional kernel modules. Let's take a more in-depth look at this in the next slide. There's a saying in computer science that any problem can be solved by adding a layer of indirection, except for the problem of having too many layers of indirection. Host-managed SMR enablement is no different. The boxes with the red text indicate where host-managed SMR enablement could be implemented in the software stack. We could implement it in a file system, block device driver, or even inside an application. Each has its own set of trade-offs. In general, higher layers will have access to more semantic and system-level information for optimization. This could lead to better performance and more room for innovation. For example, an application will have more knowledge about the importance and intent of an I/O than a block device driver. For each of the indirection layers we introduced in the previous slide, there are multiple implementations available. Here are some of them. SCSI pass-through. The Linux SCSI generic driver allows applications to send SCSI commands to a device using the Alto interface. Applications can use this interface to directly read, write, and manage host managed SMR devices. libzbc. libzbc is a user space library that provides functions for managing host managed SMR devices. Applications can be modified to compile and link against libzbc to become host managed SMR enabled. Developed by my friends at Western Digital, it is available to download from GitHub. F2FS, Flash-friendly file system, is a log structure file system that is SMR capable. With Linux kernel 4.10, F2FS can work with host-managed SMR devices when configured with the right alignment and mode parameters. Note, however, that there is a hard limitation of 16 terabyte maximum volume size. So if your total device capacity is larger than 16 terabyte, then you will need to decompose the device into smaller units for F2FS. Finally, DM-zoned. DM-zoned is a device mapper target that exports a regular block device from an underlying host-managed SMR drive. Random writes are buffered into CMR zones first and written out to SMR zones during garbage collection. Also developed by my former colleagues at Western Digital, it is available in Linux kernel from version 4.13. Now that we know the limitations and dependencies of current host-managed SMR implementations, there are multiple areas which I believe we can do better. The first thing to consider is raising the level of host-managed SMR abstraction. This gives us more semantic and system-level information, which is critical for further innovation. Knowing intent and importance of an I/O can often enable better performance and optimization. A higher abstraction level also gives us more flexibility to support and accommodate the accelerating pace of device technology advances and changes. Next, let's create a better user experience. Let's reduce the amount of complexity users have to deal with when deploying host-managed SMR. Let me explain this in more detail. As we have seen, current host-managed SMR implementations only work if certain dependencies and limitations are met. For example, F2FS requires kernels 4.10 or later and can only support up to 16 terabytes of capacity. And DM-zoned works with kernels 4.13 or greater and only supports device with specific zone configurations. All these requirements and limitations add cost and barrier to host-managed SMR adoption. Users should not have to change the kernels on all their servers when inserting a new hard disk. Next, we should eliminate the need for application changes. Applications already use well-defined interfaces, such as POSIX API for file access, REST APIs for object access, for example S3, and SCSI for block access. We should leverage these instead of asking users to modify and recompile their applications when using host-managed SMR. In addition, our storage solutions must be capable of working with all device types, so we don't create silos of storage capacity which are inefficient and inflexible. We should be able to mix and match conventional with zone devices when allocating storage. When I first started working on host-managed SMR at Western Digital back in 2012, There were a lot of debate on how we should treat host-managed SMR devices. A number of people feel that we should break host-managed SMR away from existing block device access models, as they differ from existing drives in usage model and behavior. This makes sense, as we want users to knowingly opt into these new drives that expects unconventional access patterns and active host site management. However, this means introducing a new unsupported device type and breaking existing access assumptions. While I agree with the need for a clean break, up to a point, I'm always concerned about the usability and backward compatibility of a solution. After all, it is not the developers who are using the storage, it is the users. And they don't always have the latest hardware and software. And we really shouldn't expect them to. I think this is where the host part of host-managed SMR becomes important. The host-side software should pick up the responsibility to make the experience as frictionless as possible. Finally, we need to make provision and deployment of host-managed SMR frictionless. This means being able to add and remove host-managed SMR storage capacity from anywhere at any time, without having to worry about the underlying system and hardware configuration. It also means users can easily integrate host-managed SMR storage into existing workflows and orchestration frameworks without needing to go through a separate complex provisioning process. For example, if our storage solution is dependent on a particular driver and kernel version, then our provisioning process will need to check and install the required prerequisites if needed. This could have a significant impact because these changes affect everything we have running or are planning to run on that server. We need to make sure our application and stack are compatible with the change and that our internal IT and vendors can support the new system configuration. We could, of course, wrap up the different kernel and our storage solution inside a virtual machine, but that is a potentially high overhead approach and requires extra work if our infrastructure and orchestration frameworks are mostly container-based. Over on the device side, we want our storage system to be device-friendly, so we can increase device durability and performance. This means minimizing random accesses, maximizing the size of each I/O so there are less overhead overall, prevent wearing out one head or region on the device more than others, and curtail the creation of background work for the device. Basically, we want to enable the devices to perform at their best. We will see how this will significantly improve I/O density and tail latency. Next, we want our solution to be performant and scalable, able to maintain a consistent and predictable performance at every scale. Here, we need to be cognizant that component-level variabilities and slowdowns are amplified by scale, as we have seen in earlier example on tail latency. So as we add devices and load to the system, we want to reduce contention on available resources, increase the amount of I/O concurrency, make smart prioritization decisions to maintain good quality of service, and finally, trim tail latency as much as possible to provide consistent response times. Last but not the least, we need to address future device technologies and new usage models. The pace of innovation is accelerating, and our solution needs to seamlessly support these changes so users can automatically benefit from the latest advances. It would suck if users are forced to modify their application and stack each time there's a device innovation. Let's work towards a better storage experience. At Callista, we are passionate about bringing performance and simplicity to storage. We know upcoming device technologies such as host-managed SMR, hybrid SMR, and multi-actuator will bring complexity, scalability, interoperability, and performance issues for storage users. So we designed our Phalanx storage system to address all these by being simple to use, device-friendly, and performant at scale. Let me show you how we did it. Our design goals for Phalanx are simple. We want to create a storage system that, 1, supports next-generation device technologies such as multi-actuator and zone devices. 2, performs at scale. And 3, is simple to use and just works. The first thing we set out to improve is to make sure applications can use host-managed SMR storage without modification. So we implemented a thin data access layer that enabled applications to access SMR storage using the familiar file, object, and block interfaces. Next, we simplified device management by supporting both conventional and zone devices. This enabled users to mix and match different device types, eliminating silos and maximizing utilization. We then make sure that Phalanx can be deployed with minimal dependency and limitation. We implemented Phalanx to be adaptable to different kernel versions and has no hard-coded assumption on device and zone configuration. This means you can run Phalanx without needing to check or change kernel versions, nor install additional modules. Currently, enabling host-managed SMR on a system depends on your kernel version and your ability to access and modify application source code. For example, if you're running with kernel 4.8, then you will need to modify and recompile your applications for host-managed SMR to work. With Phalanx, you don't have to worry about any of that. There are no dependencies to check, no applications to modify, and no additional kernel modules to install. We went through an intensive thought process to make Phalanx user-friendly. As both developer and users of storage, I found a lot of times user experience is just not a priority with storage systems and applications. Configuration and changes are often complex and error-prone with limitations and dependencies everywhere. And we want to change that. By removing dependencies and limitations, we made Phalanx easily virtualizable and capable of running everywhere, such as on bare metal servers, in virtual machines, and as containers. So you can easily integrate Phalanx into existing workflows and orchestration frameworks such as Kubernetes and vSphere. In addition, we made Phalanx simple to operate, with simple turnkey operations instead of complex configurations. You can see here that it takes just 2 commands to deploy Phalanx and get a system to start running with host-managed SMR. And this is what happens when we remove friction and barrier to host-managed SMR. Distributed systems such as Hadoop and Ceph become instantly host-managed SMR enabled. And much more. Again, all without any application or kernel modifications. Now, let's turn our focus to performance. We designed Phalanx from the ground up for performance and scalability. We created an innovative row and column architecture for this very purpose, so that every time a device is added to Phalanx, both capacity and performance are increased. In addition, device awareness and intelligence are built into every I/O. We will discuss what this means in a later slide. It all starts with a log-structured data layout, which enables Phalanx to minimize seeks and write contentions. We then build on top a specially designed device-aware layer that actively monitors and manages device and zone states. With this, Phalanx evenly distributes workloads across available capacity to eliminate hotspots and minimize device background work. It also makes Phalanx device-friendly, which enables devices to perform at their best. This is a core tenet of our design philosophy. We will see later how this makes a magnitude of difference in I/O density and tail latency. Performance and scalability are further enhanced when devices are arranged and written to in a round-robin fashion. We call this a write column. A write column is an elegant construct as write-ware are evenly distributed across all member devices. And with each additional member device, read concurrency is increased and read-write contention reduced. We then take everything one step further. We assemble multiple write columns into a row and column architecture, so that each time a device is added to Phalanx, performance is increased along with system capacity. Because each additional write column increases the amount of overall parallel I/O, and an increase in height of any write column reduces read-write contention and increases read concurrency. Multi-actuator devices will fit very well here, as each actuator will contribute their capacity to the system and evenly share the available workloads. Finally, because Phalanx is file and object aware, you can extract more contextual sense out of each I/O. And this makes Phalanx intelligent. It leverages user, process, and system level information to smartly prioritize I/Os and predictively optimize tiering and caching decisions. For example, Phalanx will make sure that large throughput-oriented workloads do not overwhelm small latency-sensitive ones. So what happens when we enable devices to perform at their best? Well, good things start to happen. This is a histogram of latencies when we modify a file 600,000 times using legacy software with a conventional drive. You can see here a large variation in response times, which leads to unpredictable and inconsistent performance at scale. Here is the same histogram of latencies when we use Phalanx with a host-managed SMR drive. There's a transformative difference here. The response times are not only more consistent, but also faster. Here you can see in detail the dramatic difference. At 99.99th percentile latency, Phalanx with host-managed SMR is up to 4.8 times faster than legacy software with conventional disk. As we mentioned before, component-level variabilities are amplified as systems increase in size and complexity. By curtailing the write-tail latency as we have seen here, Phalanx helps large-scale out systems maintain a consistent and predictable performance at every scale. We will see an example of how Phalanx increased Cep's write performance consistency by tenfold in the following slides. To further understand the performance impact of our device-friendly philosophy, we set up two systems to collect benchmarks for Ceph, Hadoop, and file-level I/O. One with Phalanx and host-managed SMR drives, another with legacy XFS and ext4 using conventional disks. And here's what we found. Large sequential read and writes are a natural fit for hard disks. With Phalanx, we made small random writes second nature. With a device-friendly design, Phalanx delivered 16 times more write IOPS than legacy conventional system. That is an order of a magnitude difference in I/O density, perfect for latency-sensitive workloads. And Phalanx's faster response time and shorter tail latency helped it record a tenfold gain in performance consistency and 58% higher IOPS with Ceph Rados Redbench. In addition, we also recorded a 19% faster read throughput with Hadoop test DFS-IO. There are links to more detailed benchmark results in the reference section. Please check it out. That was my last slide. Again, thanks for coming to my SDC talk. I'll leave you with a short demo video of Phalanx. Please email if you have any questions or comments. It is info@callista.io. All right, I'll see you later, and remember to be excellent to each other.